So we're finally talking about probability now that we've done some counting. And judging by the Q&A that we just went over and how long that Q&A was, my guess is you might need to go back and do some more counting practice on your own. Okay? So I had lots of problems I never picked from. You know, the end of the chapter has a ton of new problems, a bunch more odds. You know, you can see your answers in the back. Some websites have actually the answers to this textbook on even the evens, and solutions too. So find a good website that has all that stuff if you need more practice with counting. Or see me, I think I have some worksheets. Okay, anyway, we're going to be talking about probability. I don't think I need to define probability for you because it's just naturally something people understand. But not everybody's good at it. They just understand most people understand the questions. You can ask someone who's like never been educated, you know, what's the probability of winning the lottery, and they know that's low. They've never been to school in their life, but they're like, I don't think I could win that. You say, why? And they say, because there's so many people buying tickets. It's just something we understand, you know? But the problem with most people getting the wrong answers, it's usually because they don't understand the sample space. Okay, so let's talk about what sample space is. Sample space is a set of elements, it doesn't have to be numbers, which represent all the possibilities that can occur. Okay, so it could be that we're talking about this classroom. There are 26 people, so the sample space size is 26. It could be the state of California and people who bought lottery tickets, maybe 250,000 people bought lottery tickets, and therefore your sample space is 250,000 people. Okay? So it could be any of those things, or it could be something totally different like this. I'll make this a circle to make it a little bit simpler. Make these both circles here. Like, what's the probability of me shooting an arrow at this target and hitting the bullseye? Let's assume these are both circles. I'm not sure why they look stretched on your screen. They look round on my screen. Anyway, let's say they're both circles. And, you know, the small one is its own radius, and the large one is its own radius. And let's assume that the archer, or whatever, never misses the target, the actual dartboard. Okay, they're going to hit the dartboard somewhere. Don't sleep in my class. Come on. Thank you. Okay, they're going to hit the dartboard somewhere, but they might not necessarily hit the red circle. Okay, so somehow this is designed where it's impossible to miss the dartboard. Now, if I throw a marker at my board right now, trying to hit that bullseye, there's a good chance I won't even hit the big white circle. Let's see if that is true. I don't think it landed inside the white circle. It was like right here. Okay, let's try again.
Take your pop off so we can see where
No, because that'll ruin the
you hit the red.
I think I almost hit the red. Okay.
Yeah, that should be the
So the sample space on this problem is actually the area of this large circle. The sample space represents the area that could be hit, you see. So this large circle is our sample space. The small circle is more of like our target space. We call that the event space. Okay, or maybe the goal is to not hit. Maybe the goal is to not hit the red. That's a great game. I love that game. My probability is very high that I'll miss the red. I probably will win that game. Throw a dart. Don't hit the red. Okay. No problem. I win. Okay? All right. And then with of course, with my bad luck, I probably hit the red space when I'm trying not to. So you guys understand that this sample space is more geometric. Okay? In fact, if you wanted to, you could calculate this probability. You just need to know, what would you need to know about these two circles? The best thing to know would be the radius, because you really need to divide the area of the red circle by the area of the black circle, right? So you need to divide the area of the red and the area of the black. The target area over the sample area, right? So the nice thing to know here would be radius. Let's say that the radius of the small circle is 1, and the radius of the large circle is 10. Well, it's probably more like 5, you're right. Looks more like it would be 5 maybe on that scale. So how would you then find the probability of hitting the red circle? Probability of hitting the red circle, area of the red over the area of the black, right? So what's the formula for the area of a circle? Just pi r squared, right? So pi r squared, and you're going to plug in the radii. So 1 and 5. You'll notice that the pi cancels out. So we get what? 1 and 25. Yeah, 1 and 25, or 0.04. And in this classroom, we're going to always express our probabilities as either a fraction or a decimal, but not as a percentage, okay? So don't say 4%. You can say 4% chance, but don't say 4% probability. So we're going to try not to use the word percent and probability in the same sense, okay? You can say 1 in 25 chance, though, or 1 in 25 probability, or 0.04 probability, or 4% chance, okay? That's going to be the kind of rule of thumb in our classroom. So maybe if I try 4 times, I hit it once. No, probably not. If I tried it 100 times, I hit it 4 times, yeah. Tried 100 times, hit it 4 times. Okay, any questions on that? Okay, so then what's my probability of not hitting the red circle? So that's called a complementary event, and if this is called PR, you would just call that PR bar. So probability of hitting the red circle we said was 1 out of 25. The probability of not hitting the red circle is called PR bar, and that would be 24 out of 25. Naturally, you only have 2 possibilities, hitting the red or not hitting the red, and we would expect those 2 to add up to a total of 1.0, 25 out of 25. So the other day, my daughter and my son were running around in the backyard at my father-in-law's house, and they were playing mystery detective, right? So my daughter found these footprints in the flower bed, and she is positive that those footprints were not caused by the dog that lives there. She was convinced that another dog had come into the yard and was running around. So she asked Grandpa for the magnifying glass, and she and her brother, my son, and the 2 cousins were running around the backyard solving a mystery. Okay, and I think there were cat footprints involved somehow. Paw prints, excuse me. So, at the end of this, my son came up to my father-in-law and said, "We solved the mystery, or we didn't." And my father-in-law looked at me and said, "That's a probability of 1, isn't it?" That's what my son said. He said, "We solved the mystery, Grandpa, or we didn't." And I was like, that was a waste of breath.
Well,
He's 4. He's 4 years old.
That's clever. It's like, see, I'm right either way.
Yeah, I don't know if he like started a sentence and then changed his mind, you know, like we solved the mystery, Grandpa, or maybe we didn't. Or if he was actually trying to state something meaningful and it didn't quite turn out that way.
Did he actually say that?
He actually said that. I heard him say it, my father-in-law heard him say it, and we laughed because that sounds silly to us. It's unreasonable to talk about things not happening and happening. Also, we know there's a 100% chance that something can either happen or not, you know. So, anyway, it's funny, and it's a good example of what I'm talking about here. Okay, so if you go back to the notes, you can see right here I wrote this. The number of elements in the failure set plus the number of elements in the success set creates the whole sample. Okay, so right there on the paper is what my son said. In probability language, you would say the probability that event E didn't happen plus the probability that event E did happen is naturally 1.0. These 2 statements are the same. Okay? The number of failures plus the number of successes represents the number of total people available, or option things available. And this probability version of it is the same thing. Can you tell what the algebraic relationship is between these 2 equations?
Yeah.
What would you divide both sides by in this equation to get 1 on the right? What would you divide both sides by in this equation to get 1 on the right? If the right side is 1, we're dividing by what?
The number of
N of S. So that means that probability must be number of events that are desirable over number of events available or possible outcomes. So what I'm saying is you algebraically the relationship between these two equations, and you can even define probability this way. If you divide this equation by n of s, you get this one. This means probability is all up to 1. That means probability must be defined as number of elements of success divided by number of elements available. Okay, so however obvious that is to you, you can see the algebraic connection between this formula we learned and this new one we're going to create, P of E bar plus P of E equals 1. Okay? All right, so just a couple other little facts. Like down here, this formula here is really meant to only be used with equally likely outcomes. Okay? And you also know that each probability is always between 0 and 1 inclusive. It doesn't make any sense to say that the probability of losing my hat today is negative 0.4. That doesn't make any sense. Nor is it meaningful to say the probability of me losing my hat today is 1.5. That doesn't mean anything. How can the number of desirable events exceed the number of available events? That's impossible. Okay, and the sum of all probabilities is 1. We said that. Okay, so fill in the blanks and let's go on and look to our first example. Oh, before we do, real quick, do we have to use areas as a sample space in geometry? Or could we use volumes? Has anyone ever done apple bobbing? Oh, you're missing out. That is one intelligent game. I was being sarcastic. It's kind of a ridiculous game, and I'm too self-conscious to play it. Does anyone know what apple bobbing is? What is it? You've played it in kindergarten?
You go into water, like there's apples in the water, and you have to grab them with your teeth.
Yeah. You have to stick your face in the water and pull out an apple.
Awesome.
No hands. Do they make you close your eyes? Or?
Either way.
But you can't really see underwater.
Yeah, and who would want to open their water anyway? I mean, all these people with their open mouths in that water before you.
You have to go.
I wouldn't even put my face in there.
But that's kind of like a barrel too. That's kind of just like a pour.
Yeah, well, if it's chlorinated water, maybe I'd go apple bobbing.
Oh, yeah.
But then I wouldn't eat the apple.
I wouldn't want the apple. Either way, you lost.
It's a lose-lose game in my book, too. But it makes for an interesting question. Assuming the apple isn't floating on the top, but it's suspended, or it could be floating, but it doesn't have to float. It's kind of suspended in the middle somewhere. This is not really a sample space of area anymore. It's a sample space of what? Volume. There is a desirable volume called apple volume, and there is a sample space volume called water volume, and it includes the apple inside volume. So there's kind of two volumes here. Does the volume in this bucket matter? Not realistically. A person who plays this game knows to at least get their face down into the water. Okay, if somebody's up here chomping up in the air, their head's in the bucket, but they're not even facing the water, they're not really playing the game right. So you assume that everybody playing the game knows the game and won't start biting for apples until their face is in the water, right? So basically, it's going to be red volume divided by blue volume, not red volume divided by black volume, right? But this also shows up in everyday stuff. Well, not every day, but I used it in college. We were studying particles that were coming from the sun. They're cousins to the electron, called muons. Okay, maybe you've heard of them. They're heavy electrons, you could say. And they come from the sun. They go through our bodies all the time. Okay, it's a form of radiation kind of thing, you know. Stuff goes through you all the time. But we were trying to see if we could capture one of these decaying, reaching the end of its life, in our barrel of water. So we had a barrel of water in the lab, which is inside of a building, cinder block building, like these walls are cinder block. And those particles just go right through the walls and right through our barrel, like most of them. But occasionally they'll reach the end of their life while they're in our barrel. It's rare, but there's so many of them anyway. So we were just checking to see if we could catch one of them in the barrel of water. So this is like, okay, there's this volume of the world, and we got this volume of this little barrel, and what's the probability that it's going to die in our barrel? Well, the barrel was a little bit rigged. It was designed to kind of accelerate the death of these things. So we had a better probability of capturing them than just capturing them anywhere else. So this is how the neutrino was discovered too, right? The neutrino was discovered by somebody who actually was able to watch it die and see what it created or whatever, you know. So trying to capture it in a certain space, and what's the probability of that happening? That's more of a volume over volume kind of thing. Or a number line, right? I've got this number line here. It's infinitely long, right? If this number line is infinitely long, and I took a blue stick, and I just came up to the number line, and I just set it gently on the number line, and stepped away, what is the probability that I would set this 10-inch stick right on the numbers 4 through 14? What's the odds of that happening?
As close to 0 as
Yeah, this is virtually impossible. The sample space is infinitely long, and Mr. Short came along with a little 10-inch stick. What's the chances he got it exactly at 4.00000 on one end and 14 on the other end? What are the odds of that? That's practically probability 0. In fact, mathematically it is 0, because there's infinite space to work in. But realistically, it isn't 0, because there are no lines that are infinitely long. Even if they fill the universe, they're not infinitely long. So there's a finite length to every segment in this universe. And infinitely long things are only platonically real. They're not practically real. They're in your mind, but they aren't real in the hand. Real. You know? Okay, so this probably wouldn't be a 0 probability, but probably still very unlikely to do this. Let's say that the sample space was the blue, and I brought along a red segment, or let's say a red dot, and I have a little red dot, and I'd like to place it somewhere in the blue, so forget the black. Just look at the blue. What is the probability that I will take this and set it at pi in the blue region? Pi is not in the blue region. What's my probability? 0. Right. What is the probability that I will place this red dot somewhere between 4 and 14 if I'm placing it between 4 and 14? 1. Perfect probability. I'm going to place it somewhere between 4 and 14. The probability that I place it somewhere between 4 and 414 is 1. Okay? What's the probability that I place this at exactly 2 pi, which is 6.28, yada, yada, yada? It's 0 again. Why?
Pi goes on forever.
So what's the probability that I would place this point at 7.0? Let's do that.
0 again.
Why is it 0?
Because there's an infinite number of points to place down between 4 and 14.
Yeah, that's right. There's an infinite number of numbers between 4 and 14. Okay? If you include all the reals. The probability of me putting this point at 7.0 it's impossible. Okay? Now, that's in the mathematical sense. But why is it actually possible, not probable, but it is possible in the real life sense? In real life, this point is not infinitely small. Correct? There's no such thing as something you can hold in your hand that's truly infinitely small. Infinitely small is a platonic reality. It is not real. It's something you can think about. A point has no size. Draw one for me. Can't. As soon as I draw it, it's got size. If you can see it, it's not size 0. If you think about it, and it has size 0, great. That's a platonic reality. But an actual reality is there is no such thing. There's no such thing as a perfect circle. There's no such thing as a perfect triangle. There's no such thing as a straight line. They don't exist in reality. In string theory, we believe, if string theory is a valid theory of the universe, we don't believe that anything is infinitely small. Even space itself is made of something. Okay? I'm not saying I do or don't. I'm just saying, in all of our models, everything is discrete, not continuous. But in the mathematical realities, this number line really does have an infinite number of numbers on it, and that thing is infinitely small, and sticking it in the space you want is impossible. Okay? Like mathematically 0. But since this does have a little size, it has a little bit of a thickness, and there is an actual small probability that you can get it to at least sort of touch the 7 when you drop it on there. So you kind of need to know how long is this little red thing, and then you divide that by how long is the blue thing. Okay? Because that actually has size. It's a circle, it's not a dot. It's not a true point, is it? Okay? So let's do it this way. Let's say that this is a segment now, and I'm going to lay it down on the blue segment. And this segment is exactly length 2. And the blue segment is exactly length what? 10. It goes from 4 to 14. Now, what's the probability of me laying this down and it actually touches the number 7 on the number line? This is just kind of like the target problem now. You've got a small red object and you're dividing by the larger blue object. So it's just 2 over 10, 1/5. Okay? Or maybe I can make the question a little bit easier for you to understand if I did it this way. It's a point, but I'm giving you an interval, 9 to 11, and I'm saying you can place this dot anywhere in the blue. What are the chances that it ends up somewhere in this red region? So you're going to place the little red dot somewhere in the blue, and you end up laying it right here between 9 and 11. That's a 1/5 probability, because you're dividing 2 segments. You can't divide a point in a segment. You can divide a segment in a segment. Okay? You can't divide a flat shape by a volume, but you can divide 2 volumes. So you need a length and a length, and then you can divide. So the probability of this dot landing somewhere in this space is 1/5, because this is 10 inches long, that's 2 inches long. Okay? Now what if this was like time of day, and this was 4 a.m. when I started my shift at the hospital? Maybe I'm a nurse. They work long hours. What does 14 represent on time of day? 2 p.m. Right. Let's say that you got there to the hospital and you're a nurse, and your boss says, "Hey, I know you've got a 10-hour shift today. That's a lot. Take your lunch anytime you want. You got a 2-hour lunch." Sweet. 2-hour lunch, like that's awesome. That's like above and beyond state requirements. Okay? So you decide you want to take your break. What's the probability that you decided to take your break starting at some time between 9 and 11? 1/5. It's the same problem. Exact same problem. So now time is our sample space. You see? And a starting time is our event. So for you to start your break sometime between 9 and 11 is just red divided by blue, 1/5. I'm trying to convince you that probability is not always about coins and cards and things like that are countable and discrete, but rather sometimes just continuous stuff like time is ticking, or this area, and this volume. These are more geometric ideas, but they all use the same theories. And these can be like 0.5ers, right? Like this volume of this water, literally might be 32.37 cubic feet. So this would be like your denominator in your probability. And maybe the apple has volume, 0.02 cubic feet. This wouldn't happen in a classroom. If I said, what's the probability of me picking a girl, you wouldn't say, oh, well, it's 0.02 girls out of 32.37 people. Those are discrete. See, humans are counted in ones and whole units. So that's the idea of discrete versus continuous. But the same theories apply. Okay, so back to the notes. If a die is fair, so we can go back to talking about dice and stuff like that. This is more discrete now. If a die is fair, it has 6 faces, and there's no reason why it would land more on one number than another number, right? So hopefully the die in your board games at home are fair. I'm pretty sure something's wrong with my dice at home, because my wife always wins games, and I'm pretty sure it's the dice's fault. At least that's what I tell myself. Okay, so rolling a die once, there are only 6 possible outcomes. You get the 1, the 2, the 3. It's diagonal, right? The 1, the 2, the 3, the 4, the 5, or the 6. You can draw that if you want. In my sample space, I'm just going to write 1, 2, 3, 4, 5, 6. The numbers, they represent the face that's upward, of course, on the table. Because it's a fair dice, I assume that there are 6 possible cases, and that all probabilities add up to 1. So I'm thinking of a number, and if you add it 6 times, it gives you 1. and it's the same number every time. I'm thinking of 6 numbers. If you add them all up, you get 1, and they're all the same. They're 1/6. All the probabilities are 1/6, naturally. To roll a 1, it's 1/6 probability. To roll a 2, it's 1/6 probability. To roll a 3 or a 4 or a 5 or a 6, it's all 1/6 probability. Because I need 6 equally likely outcomes, and they have to add up to 1. Now, if I told you at home I have a die, and the probability of rolling a 6 is 1 in 10, you would say, well, what kind of dice is that? Well, there are some dice that have 10 faces,
Yeah.
right? Does that make sense? Now, if I told you my dice has 10 faces, and there's a 1/6 probability it'll land on a 5, something's not fair about that 10-face dice. It should be a 1/10 probability. See? So the number of faces should represent 1 over the probability, or you could say the probability should always be 1 over the number of faces. If I told you I have a 6-sided die at home, and half the time it lands on a 4, what do you know? It's a 6-sided die, just like the one in the picture, and half the time it lands on a 4.
It's a shaped dice.
Something's wrong with it. Shouldn't be landing on it half the time. What's the decimal equivalent of 1/6? What's the decimal for that? You got to know that. 0.1, yeah, 0.16 repeating. So if I told you the probability of rolling a 4 at home is 0.2, something's wrong with the dice. Right? Okay. Let's talk about coins. Now this is a weighted coin, so it is naturally an unfair coin. Actually, it's probably unnaturally an unfair coin. Somebody has been messing with it. In this problem, it says an experiment consists of tossing a coin, but the coin is weighted so that the heads is 3 times more likely to occur as tails. So I've got a coin, let's say, in my pocket, and when I flip it, it is 3 times more likely to land on heads than to land on tails. Is that normal? Is that fair? Is that a fair coin? No. Scott's searching his pockets for coins. Were you looking for a coin? No. Makes you wonder if all coins are fair, right? They use them in games, right, to choose starting teams and stuff. Are coins fair? Do they really land on heads about half the time? If you do 10,000 flips, does it land on 5,000 heads? I don't know. I don't know why we use them. I mean, they probably aren't perfectly fair, right? You probably need like a perfectly fair coin that's designed for game starting token or something. Nothing's perfectly fair, but it could get closer than a coin, right?
Yeah, but every time you have a 1 in 2 chance of getting it, so each
But how do we know that the U.S.
instance is
Treasury,
separate, though.
how do you know that the U.S. Treasury doesn't weight their coins? Or when they print the money, yeah, maybe there's like a bubble in the copper or something, and it causes like a weighting distribution thing.
You gotta watch out.
On this problem, we're supposed to discuss the probabilities P of H and P of T. So that just means what's the probability that you have a heads and a tails. So this first sentence is supposed to be an equation, okay? How would you write an equation? H is 3 times T. Can you write that? What's the equation H is 3 times T? H is 3 times T. How do you write that mathematically? Please write an equation on your paper at this time. H is 3 times T. Now, how many of you wrote this? Good. Okay, please understand we probably would want to write it this way, actually. P of H equals 3 times P of T. Because we don't want to think there's like 3 heads on the dice. Or on the coin. Coins don't have 3 heads or 3 tails, you know. It's more of a probability thing. You can tell from this sentence it's not a fair coin. Probability of heads is supposed to equal probability of tails, right? So something's wrong already, right? What did we learn on the previous page? All probabilities add up to what? 1, correct. So probability of heads plus probability of tails should add up to 1. There are only heads and tails on a die. So they add up to 1. So now we're going to solve this system of equations. This is just like solving x equals 3y and x plus y equals 1. It's the same problem. So just treat it like an algebra problem. We're trying to find p of h and p of t. So why don't we just take 3p of t and stick it in for p of h right here. So we get 3p of t plus p of t equals 1. And it's just like 3x plus x, you know. So what's 3p of t plus 1p of t? 4p of t. And this is equal to 1. So what is the probability of flipping a tails? 1/4 if you divide. That makes sense. That means that the probability of getting a heads is 3/4, which is the complement event. So notice that the numerators are ratio 3 and 1, but the denominator is 3 plus 1. See that? Because the number of elements in tails plus the number of elements in heads has to add up to the sample space, 4. So 1 plus 3 has to be 4. And 3 is 3 times more than 1. That's what those two sentences were saying. So feel free to solve them algebraically, like I just did. Okay, let's say that you meet a family and they have 3 children. Okay, this is given. There are 3 children. What is the probability that 2 of them are boys and 1 of them is a girl? Well, one thing you can do for this is to write out the sample space. All the 3-child families in the world have one of these arrangements. 3 boys, 4 parents, a boy and 2 girls, where the boy was born first. That's what my brother has. Boy and then 2 girls were born. Or maybe a girl was born and then a boy and then a girl. Or maybe 2 girls are born and then the boy. Or perhaps they have 2 boys and 1 girl. These are just families you might meet. They'll tell you their story. We went to the hospital and we had a girl. And then we went to the hospital again, we had a girl. And then we went to the hospital and we had a boy. Or you might hear different stories. I'm writing out all possible stories here. BBG, BGB, GBB, or possibly GGG. Do you want to ask a question?
Is the question asking for that they have to be in a specific order or no?
I don't see that in the question. The question is saying, what's the probability that there are 2 boys? It didn't say when they were born. So I kind of need to write out all these possible 3-child families. Every 3-child family in the whole world is one of these. There are no other options. Isn't that true?
Yeah, because it's factoring in the order they were born.
Right, but isn't it true that... Okay, listen. This is really important. This is the right sample space for this problem. Okay, this is going to be our denominator 8. 8 is the denominator of this problem, I promise you. Let's say that you didn't realize that arrangement was important here. And instead of this long sample space, watch close, you wrote this short sample space. Let's say that you thought this was the sample space. Well, they have 3 girls and no boys, or 3 boys and no girls, or 2 girls and a boy, or 2 girls and a boy, or 2 boys and a girl. And you thought there are 4 elements here, this is my denominator. Listen, that means, it is equally likely to have 3 babies born as boys as having 2 girls and a boy. No. That's not true. It is very hard to get 3 girls and a girl. Wouldn't you admit that's just naturally a less likely phenomenon? How many families do you know have 3 girls? Oh my goodness, wow, okay. Hands just went up. How many of you are from a family with 3 girls and no one else? Okay? It is much more likely to have a mixture of kids than to get 3 girls in a row. Would you agree with that statement? Okay, so shouldn't there be more examples of mixed families single gender families, if something's more likely, it should occur more times in the sample space. Isn't that true?
Yeah.
Okay, if you drew this sample space, you're going to say the number of elements is 4, and the number of ways to succeed at this experiment is 1 in 4. Look, there's only one family that has 2 boys and a girl. But you really are saying that it's equally likely to have 3 boys, or 3 girls, or 2 girls, or 2 boys, and that's just not practically true. That's just not the truth of the event, right? That long sample space was the right one. And there are 3 families in those 8 that had 2 boys. The answer is 3/8 because the sample space was wrong, see? That long one I had a minute ago was the right one. Yeah, question?
Isn't it a 1/2 probability that it's going to be a boy or a girl? So what is it, or isn't it like a 1/2 chance that it's going to be a boy or a girl? So why does it differ between the 1/3 chance between getting a boy and a girl and then maybe another boy from getting 3 boys? Isn't it just a 1/8 chance that you're going to get each one of them? Oh, I see.
Okay. I think I know what you're saying. This is why we have to be really careful with probabilities, right? If I just say the word boy and girl, you think half. All I have to do is say the word boy, and you're like half, coin half, die 6, 1 6, 1 6. 28 students, 1 28. 3 28s. Listen carefully to the question, right? Sample space always messes us up. So if you want to draw other ways of doing this, there's so many ways to do this. Let's draw this diagram. There's one couple. They take their first trip to the hospital because the baby's coming. One of 2 possibilities happened that day. A boy was born or a girl was born. Oh, another baby's on its way. Second trip to the hospital. Let's say they had a boy the first time. There are 2 possible things that could happen on this second trip to the hospital, a boy or a girl. Or if they had a girl the first time, 2 possibilities on that second trip to the hospital, boy and girl. Third trip to the hospital comes. Baby's on its way. Let's get to the hospital. Either a boy is born or a girl is born, regardless of previous outcomes. By the way, we call this independence. The fact that you are a boy or a girl will not affect the next person born in your family. Right? Can you see the 8 in this tree diagram? Where is my 8 in this tree diagram? The last column. Can you find the 3 in the tree diagram? Not everybody can. That's why most people don't like these tree diagrams. Where's the 3 that comes on the top there? Where's the 3? What? The trips, yeah. Well, not the fact that there's 3 trips, but there are 3 2 boy, 1 girl scenarios here. Can you find them? So these are more like sideways paths. So the 8 is that last column. See the 8 letters there? Here's a BBG. So one of the paths is right here, BBG. That's 2 boys and a girl. See any others? B, G, B. There's the second one. And the third one is where? G, B, B. I don't like these diagrams. I've never liked these diagrams. I stare at them and I'm like, oh, that's cool. Somebody's classifying this like visually for me. That's awesome. But where's the 8? Is this number of these guys? Where's the 3? You got to watch these paths. I don't know. I like the sample space better at the top. I can see the 3 families. Here they are. Here are the 3 families in the set of 8. And since we just got done set counting, I like the little N of S and N of E symbols. We just used them a couple days ago in the homework, right? There's another way to do this entirely. Because boys and girls are the only 2 options in the world, we call this a binomial situation. Do you guys remember the binomial theorem? Yes, you do. You do. If I asked you to cube b plus g, some of you would FOIL it out. Others would say, oh, hold on here. Mr. Short taught us this. There's going to be a b cubed and a b squared, and there's going to be a b, And then there's, with the b squared term, there's going to be a g. And with the b, there's going to be a g squared. Oh yeah, and there's a g cubed at the end. Oh yeah, and then I can get my coefficients from Pascal's triangle. 1, 3, 3, 1, you know. 1, 3, 3, 1. Can you find the 8 in this picture?
Yes.
Where's the 8?
1 plus 3 plus 3 plus
1 plus 3 plus 3 plus 1. There's your 8. Where's the 3? B squared G means 2 boys and a girl. Pretty cool. This might be your favorite way to do it. You expand the binomial B plus G cubed. The B squared G is your event. There's a 3 in front. 8 is just the sum of all coefficients. Here's your 3. Here's your 8. Wait a minute, are we saying that we can just take 3c1 divided by 2 cubed? Isn't the second number in the Pascal 1331 row also known as 3c1? Can someone explain what the 3 and the 1 and the 2 and the 3 means in the formula 3c1 over 2 cubed? Let me say that again. Can somebody explain to the class? Evidently this is just 3c1 over 2 cubed. Can you explain to me what the 3 means and what the 1 means and what the 2 means and what the 3 on the bottom means in this family? What does the 3 mean in this family? 3 children were born. What does the 1 mean? 1 girl was born. Good. What does the 2 mean?
2 boys.
There are 2 options for birth. Right? 2 genders. What does this 3 mean here? It's trips to the hospital, but it's also a number of children. So this means, look, I got 3 kids. I choose one of them to be a girl. Naturally, the other 2 are boys. And I have 2 options each time I go to the hospital. 2 times 2 times 2 to the bottom. So you can draw the sample space, count the number of elements in the event. There's 3 of them. You can draw Pascal's triangle and just add these numbers up to the denominator, and then realize that this just represents no boys, 1 boy, 2 boys, 3 boys, or no boys, no girls. I'm sorry, no girls, 1 girl, 2 girls, 3 girls. It's all the same. It's backward and forward the same anyway. Or you can expand the binomial, or you can draw a little tree. There's so many ways to do it, but it all hinges on one thing: do you know the sample space? And of course, do you understand the question? So let me just ask you a quick question. Pick any method you want. I want to know the probability of having 3 boys in a 5-child family. Okay? 5-child family, 3 boys. That's my question to you at this time. Please take a minute and figure that out. Do it any way you want. I just did it like 5 different ways for you. 5 children. That's a given. 3 are boys. Naturally then, 2 are girls. Pick any method you want. Pascal's triangle. If you have the time, write out the sample space. Use NCR. Whatever. I'll pause the recording. Anyone have an answer yet? Jack Lloyd, what'd you put?
1032 over 5 over 16.
Yeah, let's leave it like this for now. 10 over 32. Now, which of the many ways did you do it?
5c3 over 2 to the 5th.
Yeah, 5c3 means there are 5 children. We choose 3 of them, please, to be boys. 2 to the 5th means we went 5 times to the hospital, and there were 2 possible outcomes each time. Great. Okay. Anyone do it a different way? Did anyone use Pascal's triangle?
Yeah.
this fifth row, or it's technically not the fifth row, but it's the only row that has a 5 in it. The row that has a 5 in it is the 5 children scenario. So how can you use these numbers to get a 32? In other words, the denominator. Add them up. 1 plus 5 plus 10 plus 10 plus 5 plus 1. That's 32. And where is the 10 here? Right, this is the no boys family scenario. This is the 1 boy family scenario. This is the 2 boys family scenario. This is the 3 boys family scenario. Or maybe you disagree with me. Maybe you think it should start with b cubed. You know, so 3 boys first, then 2 boys, and then 1 boy.
No, 5 boys. 4
Oh, this is the 5 child family, right? This is the 5, this is the 4, this is the 3, this is the 2 boys. Fine. I'm going to go ahead it the other way around. It doesn't matter. If you have 3 boys, you have 2 girls. If you have 2 boys, you have 3 girls. It doesn't matter. It works back and forth. If you accidentally put 5C2 here because you were thinking girls, it's still 10. Okay? So there's a little bit of forgiveness with the NCR because of the duplicate numbers in the row. But 5/16, which is, what's the percentage on that? Well, what's the decimal? We're not going to use percents. Express it as a decimal. Yeah, less than 1/3, good. Point something.
point. No, point.
Let's use the calculator. So what's 10 over 32?
0.3125.
Yeah, that's right. 0.3125. And we won't use the percent, but we can use that decimal or fraction. Okay? Can you think of any other naturally binomial type things in life? We've got boys and girls at a hospital. Heads and tails on a coin. What else can you think of that might work well with Pascal's triangle? There really aren't that many. True and false on a quiz? Okay. Yeah, there's not that many real-life binomial situations, right? But it's fun to do them all these different ways. What? Win or lose? Yeah. If you exclude the option of ties, okay? Make sure you don't use Pascal's triangle on anything else, okay? Here's a coin problem. Let's just use Pascal's triangle. It's kind of the fastest way that everyone understands. I think some people might want to use NCR on this. But we have 6 coin tosses. Can someone verify that this is the right? I don't think this is quite right.
No, yeah, it is.
Is that the 6th row of, or the row of Pascal's triangle with the 6 in it?
Yeah, the one about 1, 5, 10, 10, 5, 1.
Yeah, that's right. Okay. I'll try and do it from memory. Okay, this is our row. And let's just answer the question. So what is the denominator on all 3 of these 6 coin toss problems? What's 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1? It should also be the same thing as 2 to the 6th. Okay, so all of these are going to be something out of 64, and we're going to leave them like that so we can compare them to each other. Okay, let's look at the first one. Exactly 5 heads and 1 tail. So remember, this is the h to the 6th, this is the h to the 5th, t to the 1st, h to the 4th, t squared, h to the 3rd, t cubed, h to the 2nd, t 4th, h to the 1st, t to the 5th, t to the 6th. I want 5 heads and a tail. 5 heads and a tail. Which one is that? That's a very specific situation. See, some people haven't studied probability enough to know they're allowed to do this. And so they read this as, ooh, what's the probability of getting a head? And what's the probability of getting a tail? And they try to multiply because they saw the word and. Okay, but they're just off on the wrong track. So this is probably the best way to do it. 6 out of 64. What's the probability of obtaining between 4 and 6 heads inclusive? You got to think about what that means. Literally just means 4 heads or 5 heads or 6 heads. When we're doing ORs like that, we add. So you actually should be adding a couple things together here, 3 things. 4 heads, what's my number? 15. Or 5 heads, what's my number? 6. Or 6 heads, what's my number? 1. So that comes out to 22 over 64. The more ors you find in a sentence, the more likely it is to happen. What's the probability that Mr. Shore is 31 years old, 32 years old, 33 years old, or 34 years old, or 35 years old, or 36 years old, or 37 years old, or 38 years old, or 39 years old? Pretty good chance that one of those is right. So with all the ors, your likelihood is very high. In fact, 39's probability is exactly 1 then. Okay? When you see ands, you get smaller probabilities because you're being stricter about your outcomes. This next one, what is the probability of at least 3 heads? So you got to think about what does at least mean? No less than. I'm not sure at least and no less than means the same thing. If I said I have at least $5 in my wallet, that means I have $5 or more, right? No more than means $5 or less. Both include the $5, that can't be right. Okay, let's look at this question, at least 3 heads. Could there be 3 heads? Yes. Could there be more heads? Yes. How many total on 6 coin tosses? 6 at most. So I think what they're asking us to do is count the 3 heads, 4 heads, 5 heads, and 6 heads case. See? So now you're going to include the 1, the 6, the 15, and the 20. So the 6 heads case, the 5 heads case, the 4 heads case, the 3 heads case, at least 3 heads. Okay, so that comes out to 32 now, right? No, 42. Does anyone see how I could have gone quickly from answer B to answer C? I could have just added the 20 case because B was saying 4 heads, 5 heads, or 6 heads. C was saying 3 heads or 4 heads or 5 heads or 6 heads. So all we really needed to do was add another 20 64ths to our existing 22 64ths. But it's pretty rare when you can use answer B to get answer C, you know. Okay? This next problem is a little bit weird because I made it up. All right? Somebody recently asked me a question like this, and it took me a little while to figure out, so I thought, I'm going to present this to my class. So I did. So a family is told that they can have as many puppies as they wish, as long as they keep and take care of all the puppies they end up with. The family really wants their daughter to have a female puppy. It's probably the daughter that wants it. But they know they can only afford to raise at most 3 puppies. Calculate the following. Okay, now this is a strange puppy source. Okay? Somebody's offering puppies. All right? The puppies are free. They come in the mail, actually, on your doorstep. Remember I made this scenario. It's an order a puppy online program, you see? The problem is you don't know what gender you're going to get. And it's always equally likely that you'll get a male or a female on your doorstep. Okay? So here are some possible scenarios. The family orders a puppy. The puppy shows up and it's female. The daughter is happy and it's over. They don't order anymore. Okay? Or they order a puppy and it's a male. They love the dog, they'll take care of the dog, they'll keep the dog, that's the rule. But they were hoping to get the female for the daughter. So they order again. The next puppy shows up on the doorstep and it's a female. Daughter's happy, game over. No more puppies are ordered. Third possible scenario, they order a puppy, it shows up, it's a male. They order another puppy, it shows up, it's a male. They order another puppy, it shows up, it's a female. Daughter's happy, game over. No more puppies are being ordered. Then there's, I guess you could call the worst case scenario, if you're biased against puppy gender. You order a puppy, it's male. You order another puppy, it's a male. You order another puppy, it's a male. You can't afford any more puppies. You promise to keep and take care of all these puppies. The The daughter never got what she wanted, but you can't afford to raise 4 dogs. So you're done. Game over. No more puppies are ordered. Financial reasons. Okay? There are 2 questions being asked. The first one is, what is the probability the family will end up with a female puppy? The second one is, what is the probability that the family ends up with 3 puppies? These are completely different problems with different sample spaces. Okay? Neither of them are hard, but they take some thinking. So the first question is not telling us how many times orders were done. You see that? There's no way to tell how many orders were made in this first one. Right? But you would assume it to be worst case scenario, 3. Because you want to count the number of females. So I think we can just get away with writing out that long 8-term sample space again. BBG, BBB. These are all the possible 3-puppy scenarios that exist in the world. Okay? BBB, BBG, BGB, GBB, BGG, GBG, GGB, and GGG. For part A, this is actually the correct sample space. And the number of elements is clearly 8. Okay? The question is simply, what is the probability the family will get a female puppy? Right? Female puppy, that'd be girl. 7 of these 8 are considered success. Now you might say, hold on, Mr. Shore, this doesn't make any sense. The family would never have a GBB situation. If they got the girl, they wouldn't have ordered anymore. There is no GBB, Mr. Shore. I agree with you, but the question is not asking about that. The question is just asking, what is the probability that they end up with a female? All families that make 3 male orders have this exact sample space. Right? One of them is their situation at hand. 7 of these are considered victorious, I guess. So the answer is 7/8. This has nothing to do with this particular family or their scenario or anything in their lives at all. Okay? So, part B. Part B implies that all the ordering is done, and we want to know what the chances are that they made 3 orders. Okay? In other words, they have 3 puppies. So this is an entirely different sample space. On this problem, you need to just write down the possible endings of this family's little puppy ordering career. One possibility is they ordered the puppy, it was a male, game over. The next one is they ordered a puppy, and it was they ordered a puppy and it was a girl, game over. They wanted a girl, right? Second one is they ordered a puppy, it was a boy, so they ordered another one. It's a girl, game over. Third possible case, they ordered a boy. That's not really what they wanted. They ordered another, they got a boy. They ordered another, they got the girl. Or there's that worst case scenario, they ordered a boy, or they ordered a puppy, they got boy. They ordered a puppy, they got boy. Ordered a puppy, they got boy. What is the probability that they have 3 dogs? Do not look at the sample space for part A, look at the sample space for part B. What is the probability that they have 3 dogs in the home? 2 of the 4. You see? So it's just a totally different sample space. Completely different question. Okay, any questions on that? Kind of weird, huh? So you can't use the sample space for part A to do part B, and you can't use the sample space for part B to do part A. They're just totally different scenarios. When you read a probability problem, something is being implied, and something is being asked, and you really need to think about what's being given to you. This second question is simply saying the puppy has ended up with something. That means all the three boys in a family thing, which we did earlier. You can use Pascal's triangle for part A. It's a gender question. The next one's not a gender question, is it? Part B? That's not a gender question. Okay. Okay, for this page, this part goes pretty quick. I always felt. This is where you start using some of the symbols from section 12.1. Okay? So I'm actually going to go ahead and just kind of start a separate video for this, because otherwise it'll be kind of too long for YouTube.